All right, 5.5, applications to sinusoids. Word problems, right, where the rubber meets the road. Why did we study sinusoids? They were fun in their own merit, right? But they also can describe behaviors in the real world where exponential can't describe or polynomial can't describe. They're sinusoid because they're modeling periodic functions, right? Things that come and go at regular intervals. We call things that come and go at regular intervals, we call that simple harmonic motion. Simple harmonic motion, okay? Like just the waves go in and the waves go out. The waves go in and the waves go out, right? With the tides, that's simple harmonic motion. That happens every 24 hours. Thank you, the moon, for doing that. But there are a couple of other things that we're going to talk about in the notes, and you'll discover a few more of them in the worksheet that also exhibit simple harmonic motion. Okay, the first one that I'm going to talk to you about is the classic. If you go to any old pre-cal textbook or trigonometry textbook and you look up simple harmonic motion or sinusoids, you will see what's called the Ferris wheel problem. Okay, but instead of making it just a generic Ferris wheel, I went ahead and brought it a little bit closer to home, and we're looking at the Ferris wheel at, that's right, the Comal County Fair. Okay. How many of y'all have ridden that? That's the scariest ride at the fair, huh? Right. No, it's probably one of the least scary rides. But when you get up there in the sky, you can kind of look down over the fairgrounds. It's kind of nice. The one at the fairground is a 3-minute ride. I think that's kind of maybe an exaggeration. But we'll say it's a 3-minute ride that takes its riders on the thrilling ride up to a maximum of 105 feet. So if you're scared of heights, maybe you don't ride this. And it gets you down to a low point of 5 feet. So there's this ramp that brings you up off the ground, and you get in. And when you're down at the low point, you're 5 feet above ground. All right. High point of 105, low point of 5. So you can imagine that this thing is rotating during 3 minutes. Oh, I almost caught it. There you go. And what's going to happen is it's sinusoidal, right? You're going to go up steadily to 105, back down to 5. You're going to go up to 105, back down to 5. So if we measure the height above ground as a function of time, we can model your height above ground as a sinusoidal function. Now it says assume that the Ferris wheel rotates at 6 revolutions per minute. That's kind of important. That's an angular velocity, isn't it? 6 revolutions per minute. That's omega. Tells us how fast it rotates. Assuming that the rider, you could be the rider if you want to put yourself into the problem, you become the rider. You're the last one on. The cars are all loaded. The ride is about to start. And you start, like I did on the quiz, your stopwatch as soon as the ride begins. All right, so you're timing it for 3 minutes. And you'll be the first one off, okay, for this example. The first thing that we're going to do is we're going to try and sketch the graph. Because as we saw yesterday and as you saw in the homework, if we can sketch the graph, then we can collect all of our information that we need, A, B, C, D, P, and R, and we can then write any equation we want, whether it's sine, cosine, plus or minus. So the graph is really our task. Create a nice little graph. We're going to be measuring the height in feet, so now we have units, that's important, as a function of time in seconds since the ride began. All right? So the first thing I'm going to notice is it says it's a 3-minute ride. 3 minutes is how many seconds? Approximately 180 seconds. There you go. Approximately 180. I should, you know what? Since you said approximately, I should probably make that 180.000, huh? Since we have 3 decimal accuracy here. Yeah, but it's 180 seconds. Let's go ahead and set up our X and Y axis. Our Y axis is going to be here. Leave a little space on the left. And our X axis is going to be kind of low. Okay? Because we're measuring the height in feet above ground against time in seconds. So whenever we set up a graph that has units, we also include the units on the X and Y axis. And of course, we still refer to them as the X and Y axis, right? But really it's the T and H axis. But right, it's what's an X and Y, T and H? What are variables between friends? Okay, so the X axis kind of acts like the ground, doesn't it? Because when H is 0, we're 0 feet above ground. So would you kind of be okay with me calling the X-axis the ground? Yeah, okay. So what can we mark up right away on the y-axis? Do we know the high and low point? 105 and 5. Yeah. So I'm just going to come here above there at some point. I'm going to call that 5. And then I'm going to come up here to where I want to be the maximum on my graph, and I'll call it 105. All right. So now we have the high and the low. Let's come over here and get our ABCD going. A, B, C, D, P, and R. We know the range now, don't we? We know the range. It's going to be, the height is going to be an element of the set from 5 to 105. And because there's units, I'm going to put feet on the outside. We always want to be mindful of units when we do these word problems. Okay, so we got that done. Again, on the C, we're going to wait on the C. So that's always going to be something that's going to depend on whether we call it sine or cosine. Can we get the amplitude right now? How? Oh, if I find the midpoint, I'm actually finding what letter? Not A, but what? Sinusoidal axis, which is what letter? D. All right, let's come down here, and I'll show you the midpoint formula. If you've got the midpoint formula is basically A plus B divided by 2. It's the average of the two numbers. So for us, that's 105 plus 5 divided by 2, which is half of 110, which is what? 55. Okay, so that's our D value. D is equal to 55, which means we have a sinusoidal axis at y equals 55. Okay, cool. So I can come in here and I can visually bisect that distance. And notice with notability, we can kind of maybe even adjust it. There you go. That looks good. I'm going to label that as 55. And then I'm going to come in here and I'm going to draw a horizontal line. Now, I'm going to take the time today to actually draw the sinusoidal axis with the dotted line. I'll do the dotted line just because it's a word problem and I want to kind of be as exact as possible. So there you go. Move it up. There you go. There's the dotted line. Maybe move it over a little bit. Perfect. There's the sinusoidal axis. Okay. So now what? We don't have any information, do we, on the x-axis, and that's kind of what we need. Oh, we can figure out the amplitude, can't we? Yeah, because that's now the distance from 5 to 55 or from 55 to 105, which is what? 50. So the amplitude is 50. Okay, that's looking good. So notice again, the last thing we need is B and P, and they're related to each other, yes, yes? So we don't get B from the graph. We get P from the graph, recall, and we convert it using the formula. Let's write the formula up here. B is 2 pi over P. So I need to find P. I need to find the period. Do we know what the period is? Well, 3 minutes is the length of the ride. Remember, the period could be 3 minutes, but remember, the period is defined to be the smallest amount of, in this case, time, where the values repeat themselves. I want to figure, in other words, I want to figure out how long it takes the Ferris wheel to go around how many times? Once. I need it. Well, let's think about it. It gives us the angular velocity. It says omega is 6 RPMs. Yeah, there you go. If I have 6 revolutions per minute and I'm trying to figure out how fast it takes for it to go around one time, I want to know that what 1 revolution is. Okay? So let's convert it to seconds. I won't get rid of that. I'll get rid of that. This is the same as 60 revolutions per what? 60 revolutions per, I put an S there, RPMs. That looks like seconds. 6 revolutions per. Oh, I'm sorry. Yeah, no, hang on. So what am I doing? I want to do revolutions per second. So, yeah, it's real intuitive, isn't it? You can almost figure it out. 10 revolutions per 1 minute. I want to figure out. 10 seconds per 1 revolution. Yes, let's convert it to seconds. Okay, so bless you. So 1 minute. This is what I wanted to do. I want to divide by 60 seconds. Okay, boom. So now I get 6 revolutions per 60 seconds. That simplifies to 1 revolution per what? 10 seconds. Yeah. It is. I made the numbers up. I made the Carney kind of like lean into that handle a little bit more because it's a Ferris wheel after all, and it's kind of boring. But if you really get it spinning fast, then the fact that the bolts might not be all the way tight makes the ride a lot more thrilling. Yeah, it is spinning pretty quickly. Now, what we want, we don't really want omega here, 1 revolutions per 10 seconds. What we really want is 10 seconds per 1 revolution. Okay? Which is fine. If you want to take the reciprocal of omega, instead of 1 revolution per 60 seconds, you got 60 seconds per 6 revolutions. Okay, and that gives you 10 seconds per revolution. So in the future, if you want to figure out what the unit is for 1 revolution, take the reciprocal of your angular velocity. Okay. Now, what is that? 10 seconds for 1 revolution. That's the what? That's the period. Okay. So let's come down here and say the period is 1 over omega, assuming that your units are correct. And in this case, it's 10 seconds, which, yeah, it is kind of fast. In reality, maybe it goes around once every 30 seconds, maybe. Some of the big ones, like the giant, like the one in Orlando and the one in, we'll say Paris, France, they call them like sky wheels or something. They go around like once every like 30 minutes. They rotate very, very slowly. Okay. This one goes around pretty fast, dangerously fast. Okay, so now here's the thing. I want to start making marks on my x-axis. So here's what we have to decide. I need some indication in the problem as to where to start. That's going to establish a point of reference on the graph. Does it tell us where the rider starts? He starts at the bottom. Yeah, he starts at the bottom, at the low point. So this is kind of nice. At t equals 0, I can put a dot right there at 5. And I know that that's going to be one of my critical values. Yes, yes? Okay, so this is the easy one where there's no horizontal shift. The guy was smart enough to start his watch at the bottom. And so now I can come out here. I'm just going to come out here, and I'm going to put the period to be 10 seconds. And then half of that is 5. And then half of that is what? 2.5. What's the most important number on this entire ride? 2.5 seconds, okay? Every 2.5 seconds, which is kind of fast, he's going from a low to a mid to a high to a mid to a low. It's pretty fast, okay? So let's go ahead and establish this distance then for some more ordered pairs. Now remember, I always want you to put 1 negative ordered pair. In this case, it doesn't really make sense because the ride was stopped. But we're going to go ahead and put 1 point backwards. I always want you to include 1 ordered pair. Really, for this problem though, t is greater than or equal to 0. In fact, you know what? Let's not even put a point there. We don't need one here. Okay? T is greater than or equal to 0. He started his stopwatch at the right time. All right, now I'm going to go ahead and finish, erasing everything, apparently. I'm going to go ahead and put the rest of the marks down. I'm going to try and eyeball them. And then I'll come back and number them later. That looks good. All right, so now I just keep adding 2.5, right? So after 5, I get 7.5, and then 10, and then 12.5, and then 15, and then 17.5, and then 20, and then 22.5, and then 25, 27.5, kind of running out of room here to write, and then 30. So I was able to get the full ride on my axis. You see that? I got 3 cycles is what I got. I got 3 cycles. Ooh, that is kind of fast. All right, now I can finish putting my dots, right? I have low, axis, high, axis, low. Now when you come low, Remember, when you go low, you're not going to the x-axis, are you? You're going down to 5. So when you're drawing this, it should have certain look of symmetry to it. And then you connect the dots with these nice quarter cycle arcs. And as you're doing this, you can almost imagine that you're on the ride. I'm going up, whee, hit the high point, coming back down. Wow, so I've got 30 seconds. I've got 30 seconds mapped, and I went up and down 3 times in 30 seconds. That's fast. That might actually be a pretty fun Ferris wheel when you're going that fast, right? You can feel the G forces maybe. Do we know what the diameter of the wheel is? 100 feet? Yeah, 100 feet, because that's the distance from the high to the low, right? So the amplitude must be the what of the Ferris wheel? It's the radius. Yeah. So we can start making these connections to the real world. The ground is the x-axis. The amplitude is the radius of the wheel. The angular velocity is the speed, if you will, of the wheel, how fast it rotates. There's no thrill factor here, but we know that it's going pretty fast, so I would rate the thrill factor probably as a 10. It's always more exciting, too, when it's the local carnival, because they put those things together so fast, and they do it so often that sometimes it's easy to get careless, and you really don't know if they're secure enough, you know. But that just adds to the thrill, if you ask me. All right, I'm going to turn the corner here and keep it going because I know the ride continues on. All right, now that we have the graph, is it easy to write the equation? Bless you. Yeah. Okay. So let's go ahead and do it. I'm going to call it h of t instead of f of x. And I heard someone say already, maybe it was Brady, what would be the easiest equation to write for this one if we have a critical value at 0? A negative cosine, right? So to avoid a phase shift, which just makes the equation a little bit more complicated looking, let's start at 0, no phase shift, and because it's a low point, we'll call it negative cosine. So we have a negative 50 cosine of the b value. Have we found the b value yet? Yeah, it's 2 pi over 10, which simplifies to pi fifth. Yeah, so I need it now. I can find it when I need it. That's fine. Pi fifths. And then I'm just going to put t. There's no horizontal shift. So we don't need the extra set of parentheses. And then it's plus 55. And there's the equation.
You don't have to state where, because it's negative at a low point. You don't have to state a low point.
No. No. Yeah. No, you don't. Yeah. Remember, there's infinitely many. Just because you started at a low point doesn't mean we have to write it as a negative cosine. We could have like done a positive sign and shifted over to 2.5, and it gives us the exact same graph. Okay. But the fact that 0 was a critical value, to avoid a phase shift, which just makes your equation look nicer, we'll just do a negative cosine because it's a low point. Okay, now everybody go to your Minnesota calculator, or if you feel like standing up to stretch, you can grab a yellow one. But I'm gonna sit here still, and I'm gonna go to Minnesota, the trusty old Minnesota link. Come on, Minnesota, you can do it. Go ahead and type, if you got your equation calculator loaded, go ahead and type it into Y1. This section is primarily going to be a calculator section. But notice we didn't pick up the calculator until we had the graph and the equation all stated in front of us. Okay, but now to answer the questions, we're going to use the calculator. Now, the first thing you should check when you have your calculator is the mode, right? Hopefully it's reset. Someone turned it in, it's reset. But what mode should we be in? We should be in radian mode. Now, let's talk about the importance of radian mode. When you have a normal sinusoidal function, like in the previous section, the x-axis was always the angle, and that was in radians, so it was unitless. And the y-axis was always the sine of the cosine ratio, which was also unitless. So there were no units on the x or the y-axis in the previous section when we were graphing sinusoids. What that allows us to do then is when we find behavior that can be modeled by a sinusoidal equation, we can assign units to the x and y axis because there's previously none there. If we were in degree mode, we're hopeless. We can't measure time on the x-axis if we're in degrees. But because we have unitless ratios and unitless radians, we can assign height and time, respectively. Okay, so I'm going to go to radians, and I'm already highlighted, so now I'm going to click y equals, and let's type in this function, negative 50 cosine of pi fifths, so alpha x, that's your horizontal division bar, pi fifths, and then, of course, we use x instead of t, close parentheses, plus 55. Now, don't hit zoom 6, don't hit graph, because we have the window right in front of us that we want to graph it in. So now go to window, and let's type in the same window we have here. On the x-axis, x-min, let's go from 0 to x-max, let's go to 30. And then your x-scale, you can leave it at 1, but what are we actually counting by? You want to change it to 2.5? You don't have to. You can leave it at 1. It really doesn't matter. But since we're counting by 2.5s, I'll put it at 2.5. Now, here's where you want to actually go a little bit above and below what we have, because the calculator uses the bottom and the top of the screen to give you information. So let's, instead of going from 5 to 105, let's go from negative 10 looks good. And then instead of 105, let's go to like 115 or 120. We'll just go 10 units above and below. And then your Y scale, if you want to leave it at 1, that's fine. You'll get a fat axis. I like to just turn it off at 0. We really don't even need marks on the y-axis. So leave it at 1 or turn it to 0, and now hit graph. Do we see similarly what we have drawn? Yeah, that means that we've done it correctly, and that means our calculator's in the right mode. It means we've typed it in correctly. That's a good sign, isn't it? Actually, it's a good negative cosine. But it could be a good sign too, yeah? Yeah. Trig joke. They're hard to come by. Now that we have the equation and the graph and we verified it on the calculator, now we can start answering the questions, okay? Part B. Part B. Oh, that's what we did, part B. We're on part C now, okay? So this is answering the question. How high above the ground is the rider at 48.5 seconds? How high above the ground is he at 48.5 seconds? Now, if you recall from our logistic days, our exponential days, there's really only two ways to use this type of problem. I either give you the input and you plug it in and chug it and you find the output. You just evaluate it. That would be me giving you a time value. Or I can give you the Y value, I can give you the height and ask you when he was at that height. For that one, we would have to draw the Y value and find the points of intersection. That's it. I give you the input, you plug and chug, give me the output. I give you the output, you graph it and find the input with the intersection. What did I do on part C? Did I give you an input or an output? I gave you an input, didn't I? 48.5 is time. So there's two ways to do it. Remember, from your graphing screen, if you hit 48.5, yeah, you're going to get error, right? Oh, why? Why are we getting an error? Because our graph on the x-axis only goes to what? 30. So you have two options here. You can extend your window to go to something beyond 48.5 and then watch it graph again. Or the better way, remember, is just to go to the home screen, second quit, and go alpha trace number 1. Recall it on the home screen, put your parentheses there, and just type in 48.5. Boom. And there we go. So I'm going to come down here and say H. I'll use a different flavor here. This is part C. H of 48.5. That's all you have to show me on your paper. If you put H of 48.5, I know exactly what you're doing. If you leave off H of 48.5 and you just put the answer, I don't know how you got it. I'm going to play stupid, and you're not communicating your result, and you're not going to get credit. All right, how many decimals do we report if it doesn't terminate? 3. So 25.610 or 611. I don't care. Round or truncate. Now, this is a unit, a live problem. So what units are those? Seconds or feet? Feet, right? It's an output, so it's feet. So basically, if you were writing a sentence to interpret it, you would say at 48.5 seconds. In fact, let's do that. If I had you to explain the meaning of your answer in a sentence, you would say you would answer like an engineer, at 48.5 seconds, comma, the rider is 25.610 feet above ground And then the follow-up question might be, at this time, is the rider going up or down? That is the follow-up question. At this time, is the rider going up or down? Now, that is where finding it on the graph has its advantage. If you would have changed the window to include 48.5 and trace enter, you would see it blinking on the graph. And you'd be able to tell just where it's blinking if it's going up or down. We don't have that, and we don't need to go back and do that after the fact. There is a way to determine if he's going up or down from the home screen. Any ideas how we could do that? Pick a value to the right of 48.5. Now, to be careful, do you want to use 49 or 50 or 60 or what should we use? I would go 48.51. Yeah. I would go like a tenth or a hundredth even to the right, because if you go too far to the right, you can actually have turned the corner and you're already heading back up when you're really heading down. So here's what I would do. Alpha trace, number one, I would say 48.51. Let's go a hundredth of a second in the future, and then I just compare those answers. And you should be pretty safe if you go a hundredth of a second in the future. So in the future, I'm what, higher or lower? I'm lower, so you must be going what? Down. So I'm going to say the rider is 25.61 feet above ground, comma, heading down. So I will have you write the equation, the sentence that explains the meaning of your answer. Okay, at 48.5 seconds, comma, the rider is 25.61 feet above ground, comma, heading down. There we go. So we have our numeric answer. That's the top line, our numeric answer. With notation, I better say that, with notation, correct notation. That's going to be a check. And then you have your sentence answer. And I'm going to go ahead and say with units. That's the next check. Notice when I say with units, it's units on both of them, isn't it? You have seconds and you have feet. If you just said at 48.5 and you didn't say seconds, you would lose the check. No, because it's an input. Right, that's a good question. You just need them on your output. Good question. In fact, here's the way that I usually grade it. Since it is a numeric and a sentence answer, if you left off feet on your numeric answer, I wouldn't count off. Because guess what? You're recovering in your sentence. You're telling me what the units of 25.61 are. Okay? So you would get away with it. And I'd be fine with that. But to establish good habits, you should get in the habit always of putting your units on your final numeric answer, because there's not always a follow-up question that says to explain the meaning of your answer in a sentence. And so that has to stand alone by itself. But you don't have to leave the units. You don't need the units on your input. No units needed right here. All right. And so I could do that same thing for now anytime. You give me any time during the ride, and I can figure out where he was going up or down. Yes, yes? We have this now technique that we can use for any time. Give me any time, I'll find it. All right, cool. At what positive time, part D, is the rider 88 feet above ground? So now I'm giving you the output. Yes, yes? Coming down for what? The third time. That gives me something very specific to look at. All right, so let's come over here. What am I going to have to show to get credit on part D? What am I going to have to show to get credit? I'm going to have to show H of T, not H of whatever the answer is. Some people put H of the answer. We put H of T equals 88. Okay, and if you want to put a feet there, you can. That's your check for your numeric setup. And then underneath there, we're going to put T equals. And we're going to write the answer. So I want to know when the height is 88. And then underneath there, that occurs when the time is what? So now we go to the calculator, and in Y2, we type 88. And if we hit graph, we'll see, at least within the first 30 seconds, we'll see all the times that's at 88 feet, right? Or you're at 88 feet. We'll put you on the right. You're at 88 feet 4 times during a 30-second time. Again, as Ryan pointed out right away, it's kind of fast. It might be kind of fun. All right, so which of those, if any, points of intersection am I looking for? I'm looking for the third time coming down, right? Which is actually the sixth point of intersection, isn't it? I'm going up, then I'm going down. I'm going up, then I'm going down. I'm going up and going down. So at least I don't have to adjust my window because I can see the third time coming down on my graphing screen. You would have to adjust your window if I had asked like the third time coming down for the fourth time. Or you would have to know where it was the first time and just add full cycles to it. Remember, all of those points of intersection where it's coming down are how far apart from each other? No. Nope. Every point where it intersects coming down is how far apart from each other. Say 10. 10. Why 10? 10 is the what? That's the period. That's where the graph returns. Every point on that graph where it's intersecting going up is how far apart from each other. 10. 10. 10 is the period. So corresponding points on different cycles are just multiples of periods away from each other. Okay? So anyway, let's find it. Second trace. Second trace. Now I'm locked in. Let's try it again. Let's reload it. Second trace number 5. And now I have to hit enter, enter. That just communicates that I've got my first curve and my second curve. And then for the guess, we do have to scroll closer to that one, right? Because there's 6 points of intersection. It doesn't matter when you say first curve, second curve. You can just hit enter, enter. But for your guess, you got to scroll closer to the one we want. And then I hit enter, and what does it tell me? 26.352 or 353, either one. Again, I'm a big truncator, so 26.352. And then that's my final numeric answer, so what should I put on there? Seconds, yeah. Now again, if you wanted to write the sentence, you don't need a period. You would say, the rider is at 88 feet coming down for the third time at 26.352 seconds. Okay? All right, but we're not going to write a sentence there. All right, here's a good one. I'll use purple for this one. During the 3 minty ride, look, it says minty ride. Oh my gosh. I'm going to fire my editor. During the 3-minute ride, that's how long the ride lasts, for how many seconds was the rider above 100 feet? Show the work that leads to your answer. So for the full 3-minute ride, we're above 100 feet for a certain amount of time. Would you agree? We need to figure out how long that is. So the first thing that I'm going to do is I'm going to say h of t. You can say either equals 100, or to get credit, you could say h of t is what? Bigger than 100. I don't care which one of those you put. But that's going to give me the indication of what you're doing. Either one of those, okay? Now what we do is we go back to y2, and I'm going to look at 100 instead of 88. Now, here's what I'm going to do. I don't want to change my window to 180. Watch this. If I change my X max to 180, I'll see the entire ride. That's a lot, right? Now, you could count how many cycles are we above 100 during this 3-minute ride. You would have to count how many peaks we have. How many peaks do we have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. We could figure that out as well from the first screen, okay? So there's 18 times where we're above 100 for a length of time. The other way to do it, which I would recommend, is just go to your window and just go to a 1 minute, okay? Go for 1 minute, which is 60 seconds. And now you're counting how many times how many peaks do we have? 1, 2, 3, 4, 5, 6. And then, of course, 6 times 3 is what? 18, okay? So I'm just going to make it, this is a note to myself, okay? We have 18 cycles where we're above 100 feet. Those should all be symmetrical to each other, yes, yes? Because it's simple harmonic motion. If I can find the length of time between 2 consecutive points of intersections where I'm above, all I have to do is multiply that by 18, right? Would you agree? Because of the symmetry? So let's go ahead and let's use the first one. Okay. So I'm going to go ahead and say t sub 1 equals and t sub 2 equals. I'm finding two values of time now. So I'm going to hit second trace number 5, enter, enter, and I'm going to scroll way over here, and I'm going to find the smaller of the two first. So I'm going to make sure I'm closer to the one on the left. I'm going to hit enter, and it gives me the intersection to be 4.282. Now, guess what? I want to use that value later on, but I don't want to have rounding error. So I need to store that value. So I'm going to store that one as A. And I'm going to put A on my paper. So now I go to the home screen, and I hit X stow alpha A. It temporarily stores it as X. So hit X stow. Stow is just to the left of 1, alpha A. And now it's in there as A. It's not going to be overwritten when I go back to the graphing screen, right? I stored it with all of the decimals as A. And then I go back and I find the second point of intersection. Second trace number 5, enter, enter. Now I scroll a little bit more to the right, hit enter, and it gives me the second one to be 5.717. So I still report it to 3 decimals. I'm going to store that one as, guess what? B. So I go back to the home screen and I hit X stow alpha B. Oops, alpha B. Boom, and there it is. I've got it. Now, all I need to do to figure out the duration between those two times is do what with them? Subtract. So here's my final answer. I'm going to say h of t is greater than, or I'll just write the sentence. Let's just, because we already showed the setup. We don't have to do it again. We'll just say, so the rider is above 100 feet for, and then we'll do the calculation right here. It's 18 times b minus a, which equals, isn't that all we have to type in? 18 times b minus a? All right, let's type that into the home screen. 18 parentheses, alpha b minus alpha a, close parentheses. Boom. And then we'll just say that equals 25.841 or 8.2, either one, round or truncate, seconds. And you can abbreviate seconds SEC if you want. There you go. This is what it means when it shows the work, show the work that leads to your answer. When it requests this, show the work that leads to your answer. Show the work that leads to your answer. What it's looking for is this. It's looking for the first t value, it's looking for the second t value, and then it's looking to see what you did with those. That communicates to anybody, including me, especially me, what you're doing. Okay, what's the linear velocity of the rider in miles per hour as the Ferris wheel rotates? Okay, so if you think about the linear velocity, we're not going to have time to do that. We're going to have to do that one tomorrow, okay? That's basically what he's feeling as he's out there in his car and he's going through space. In other words, if that wheel were to break off and he were to fly off in a straight line, how fast would he be flying off of that Ferris wheel? We'll start there tomorrow. Okay. You see how much fun this is? Did y'all have a good time on the Ferris wheel at the Comal County Fair today? Go ahead and reset your calculator so the next class doesn't have the window or the equation.